Hi guys, in the last lecture what we covered is we started moving from the ideal transformer towards the practical transformer by removing the some assumptions that we made one by one. So first we saw what happens if we consider finite permeability in a transformer. There we saw induced EMF equation, that is 4.44 Fn Bm into area. This was the induced EMF in case of transformer. For primary we will use the primary number of turns, and for secondary we will use secondary number of turns. And also we saw that there is existence of a magnetizing current to develop the flux. Then we removed the assumption that the transformer has zero iron losses. And to compensate iron losses we assumed a current IW. And we called that no load current is under root IW square plus I mu square. This was my no load current in case of transformer, that is the current drawn by primary winding even when no load is connected at the secondary winding. Then we considered the case of loaded transformer. There we saw when primary draws a current, it develops a flux which tends to oppose the primary flux. So primary winding draws an additional current I1 dash such that N1 I1 dash is equal to N2 I2, so that it cancels the secondary MMF and flux in a transformer is constant. So transformer can be treated as a constant flux device. Okay. In this lecture we will remove other two assumptions. One was winding resistance and other was leakage flux. So let us first consider the winding resistance in case of transformer. Now due to winding resistance, when current is flowing in the winding, there will be some losses. So winding resistance has been represented by R1 in the primary and R2 in the secondary winding. Now these resistances will have two effects. First effect is voltage drop, which is equal to I into R. Next is the ohmic loss, which is equal to I square R. So due to these resistances there are two effects. One is the voltage drop between the applied voltage and the induced EMF. Other is the ohmic loss, which is equal to I square into R. This loss is called as copper loss. Why? Because it is occurring in the winding which is made of copper. So it is called as copper loss. Now if we apply the equation or the KVL, then I can write down V1 is equal to minus E1 plus I1 R1. Okay, because the voltage drop between V1 and minus E1 would be I1 into R1. Similarly, we can write down on the secondary side E2 is equal to V2 plus I2 R2, because the voltage drop between EMF E2 and voltage V2 is I2 into R2. Now the copper loss would be, in primary winding it will be I1 square R1, in secondary winding it would be I2 square R2. Now my motive is to bring this resistance R2 into the primary winding. I want to develop a circuit model such that this R2 can be included in the primary winding. So the criterion that I use to transfer the resistance from secondary to primary is the copper loss must remain same, because no matter what circuit model you are using, the transformer is not changing, so its losses must not also change. That is the criterion that we will be using to transfer the resistance. Okay, are you getting me? Because whatever the circuit we draw is hypothetical. Transformer does not have any such circuit. That is what we are approximating the transformer by a electrical circuit. So no matter whatever circuit I am drawing, the physical phenomena occurring in the transformer must not change. That is why what I am saying is copper loss must remain same even after the transfer of resistance. So if I transfer the resistance, let us say it becomes R2 dash, then copper loss will be I1 square R2 dash, because now R2 dash will be lying in the primary winding. It must be equal to I2 square R2. So what I will write, R2 dash is equal to I2 by I1 square into R2, which is equal to N1 by N2 square into R2. Here what I have done is I have neglected the no load current. That is why ratio of currents is equal to inverse ratio of the turns. So it is R2 by K square, where K is the transformation ratio. K is equal to N2 by N1. Similarly, what we can do is we can transfer the primary resistance to the secondary on the same basis. So what I will write, I1 square R1 should be equal to I2 square R1 dash. Now R1 dash is equal to I1 by I2 whole square into R1, which is equal to N2 by N1 whole square into R1 into K square. So that is how we can transfer the primary resistance to the secondary. So by to transfer the resistance from one winding to another, we have to multiply the resistance by the turns ratio square. In the numerator, the turns should be of the side where you are transferring the resistance to. Like in this case, I was transferring the secondary resistance to primary resistance, or secondary resistance to primary. So in the numerator we had primary number of turns, and in the denominator we had secondary number of turns. In this case, in the second case, we were transferring the primary resistance to secondary. So in the numerator we had secondary turns, in the denominator we had primary turns. So that is how we transfer the resistance from one winding to another winding. Now after transferring the resistance from secondary to primary or from primary to secondary, we can add both the resistances. Now we have two resistance in primary winding, so equivalent resistance will be represented by R01. It will be R1 plus R2 dash, which is R1 plus R2 by K square. Similarly, in secondary winding, we can write the resistance as R2 plus R1 dash, which is R2 plus R1 into K square. This is the equivalent resistance referred to primary, or the equivalent resistance referred to the secondary winding. So total copper loss can now be written as I1 square into R01 or I2 square into R02. Remember, you have to use only one of these, because either you have referred the entire resistance to the primary winding or the entire resistance to the secondary winding, but not both. So you cannot use R01 and R02 at the same time. You have to consider either one of these. But what is the benefit of transferring the resistance is we have transferred the entire resistance on one side, so analysis will become simpler. Now we do not have to consider two voltage drop or two copper losses. We can consider only a single voltage drop and a single copper loss. So that is the effect of winding resistance. Next, let us consider the leakage flux. First of all, what is meant by leakage flux? Leakage flux is nothing but it is the flux which links only one of the two windings of the transformer but not both. Okay, that is, it can be in either primary or secondary but not both. It can link only one winding. Why is it so? When current is flowing in a winding, the flux lines will be passing through the core, as well as some of the flux lines will be passing through this air gap, like this. This flux which passes through the air gap and not through the core will be called as leakage flux. So this flux will depend on the current carried by the coil. And usually what we consider is, we consider that the flux developed by the coil, or the leakage flux, will be in the same phase as the current. As I told you in the last lecture also, the flux and current producing the flux are in same phase. Okay, always remember this, the current producing the flux and the flux produced will always be in the same phase. Now, due to this leakage flux, there will be some EMF induced. That EMF induced will be considered as a voltage drop in case of the transformer, because every EMF will lead to a current every flux will lead to a EMF minus d phi by dt into number of turns according to the Lenz's law. Okay, so what we do is we consider this EMF as a voltage drop in the circuit. And how do we consider that voltage drop is? We consider that voltage drop something like this: V1 bar is equal to minus E1 bar plus J I1 X1. We consider that voltage drop by a reactance. Okay. Similarly, E2 bar is equal to V2 bar plus J I2 X2. So whatever we are doing is we are just considering a reactance in the primary and the secondary circuit to account for the leakage flux. So this reactance can be called as leakage reactance. Okay. If we consider both resistance as well as reactance, then we can write down V1 minus E1 plus I1 R1 plus J X1, that is minus E1 plus I1 into Z1. Similarly, E2 will be V2 plus I2 into Z2. So these two equations we can consider when we are considering the winding resistance as well as leakage reactance simultaneously. Okay. So let us represent the phasor of this entire circuit now that we have considered every non-ideality. First we will take I mu, then we will take flux, then we will take induced EMF E1, then we will take induced EMF E2, then I will take minus E1, and in the same phase I will take loss component of the current IW, and the sum of these two currents will give me no load current I0. And with E2 I will take the current I2, let us say I2, and in the opposite phase we will consider the current I1 dash, that is KI2, and the sum of this current and the no load current will give me I1. Now due to this I2 we will have the leakage flux phi L2. Due to this current I1 we will have leakage flux phi L1. Okay. So now due to these fluxes we will have some voltages induced. Voltage induced due to any flux is 90-degree lagging with respect to that flux. So that is what we will have EX2 here and EX1 here. That is, the voltages are lagging the fluxes by 90-degree. 90-degree lagging means 90-degree in the clockwise direction. Now as we wrote down the equation we need to find V1 and V2. Now V1 was minus E1 plus I1 R1 plus J I1 X1. So I1 R1 will be in the same phase as I1. This will be my I1 R1. Then J I1 X1 will be like this, J I1 X1. So this net phasor would give me V1. Okay. Similarly, to find V2, V2 will be E2 minus JI2R2 minus JI2X2. E2 minus JI2R2, it will be like this. Minus I2 R2 minus JI2X2. I2X2 will be 90 degree in the anti-clockwise direction. Then minus JI2X2 will be like this. So the net phasor, this will give me V2. Okay. So that is how we can find the V1 and V2 from E1 and E2. Okay. Just I have applied the equations of KVL. So this is my entire circuit. Now if you see this JI1X1 is opposite to this EMF. That means JI1X1 compensates the effect of leakage EMF. So the reactances, the leakage reactances do compensate the effect of the leakage EMF that is developed due to the leakage flux. Now like resistances, we can refer the reactances on both the sides of the transformer. So X2 dash or the reactance X2 referred to the primary will be X2 by K square. Similarly, reactance X1 referred to the secondary will be X1 into K square. So that means just like reactance resistances, we can refer the reactances. So I can directly say we can refer the impedance. We can refer the impedance from one side to the other side. Now that we have considered all the non-idealities, let us try to develop the equivalent circuit of the transformer. So exact equivalent circuit looks something like this. This is my primary winding resistance, primary leakage reactance. This is my core loss resistance, this is my magnetizing inductance. So if you see, the core loss resistance and magnetizing inductance are connected in parallel with E1. So this IW, that the current will be going into the core loss resistance, will be in same phase as E1, and I mu, the current going into the magnetizing reactance, will be 90 degree lagging by minus E1. We saw in the phasor also, minus E1 was like this, I mu was like this, and IW was in the same phase. Okay. Then in the secondary winding, we have the secondary winding resistance and the secondary leakage reactance. And the windings have number of turns ratio N1 is to N2. We have connected a load impedance ZL, and across the load impedance we have the voltage V2. Across the winding EMF E2, across the winding EMF E1. Now this is the exact equivalent circuit of the transformer, and it is not so easy to solve, because we have to form the KVL equation on both the sides and then solve the circuit. So solving two equations is quite cumbersome. Then what to do is, why not refer the entire circuit on one side of the transformer? I know if we transfer the secondary impedance to the primary, then Z primary can be written as Z secondary by K square. That relation we derived just now, where K is nothing but N2 by N1. So if we refer the circuit to the primary winding, then we have to form only one equation that will ease our effort. So how to refer is, the primary windings remain same, the secondary winding will be something like this. Here we will have R2 dash. What is R2 dash? R2 dash is R2 by K square. Then X2 dash is X2 by K square. Now we had the load impedance, so what to do is, we will connect the load impedance like this. Here this will be ZL dash, ZL dash will be ZL by K square. Now if you see, the entire circuit is on one side, we can easily solve the circuit. Okay, so that is how we will solve the circuit, and the voltage across ZL dash will be V2 dash. V2 dash is nothing but V2 into N1 by N2. Okay, so this will be my V2 dash. So we can find V2 dash, and then we can find V2 by this relation. So finding V2 dash is quite easy now, since the entire circuit is on one side. So it is just a network problem to solve this circuit. Now to further simplify the circuit, we try to make some approximation. What we do is, we transfer this shunt branch from E1 to the V1 side. Earlier, if you see, the voltage across the shunt branch is E1. As I told you here also, the voltage across the shunt branch is E1. Now we are referring this here, or we are moving this branch directly here from E1 to V1. Okay. And then this resistance R1 and R2 dash will be in series, and X1 and X2 dash will also be in series. This will be R01, this will be X01. So now to simplify the circuit, it is very easy. Since we know the voltage V1, we can find I0, and voltage V1 is applied across this combination also. So it is quite easy to simplify or quite easy to solve. Now let us see what are the effects of our approximation. Now suppose we consider the no load condition. If we are considering the no load condition, then this ZL dash will not be there. So this will be open circuit. The entire current I1 will be equal to I0. Under no load condition, I1 will be equal to I0. So if we consider the exact circuit, when I1 will be equal to I0, V1 is the voltage here, E1 is the voltage here. So I can say V1 minus E1 will be equal to I0 into Z1. There will be a voltage drop I0 into Z1. Z1 is the impedance R1 plus J X1. But now if you consider this circuit here, we will see that V1 will be equal to E1. There will be no voltage drop in the circuit. So what I will say is, no load voltage drop is neglected. Okay, by making this approximation, we have neglected any no load voltage drop. Similarly, when we had the exact circuit, under no load condition, I0 was flowing through R1. So copper losses would be I0 square R1. But in this circuit, if you consider no load condition, the current going through here is 0. So there are no copper losses. So I0 square into R1 is 0. We have not considered any no load copper loss. Also, what we have is V1 will always be greater than E1. Why? Because due to the voltage drop between V1 and E1. So we have shifted the shunt branch from E1 to V1. That is, we have shifted the shunt branch from a lower voltage to the higher voltage, due to which these currents will also increase. IW will increase and I mu will also increase, because IW is now V1 by R0. Earlier it was E1 by R0. So IW will increase because V1 is greater than E1. So IW will increase, which means more core losses. I mu will increase, which means more magnetizing current. So core losses and the magnetizing current in this circuit are overestimated. They are more than the actual value. Actual value was dependent upon E1. By approximation, we are taking it to be V1. So we are taking more than the actual value. So we will call it as overestimated. So let us summarize what we have learnt in this lecture. We considered the first of all winding resistance, and we saw to refer the resistance to the primary winding, R1 dash will be R1 into K square, transferring the primary resistance to secondary, and transferring the secondary resistance to primary will be R2 by K square. Then we saw leakage flux, and we saw that due to leakage flux there is EMF induced, which can be compensated by JIX. That is the voltage drop across a reactance. So we consider the series reactance on both primary as well as secondary side. And similar to this, we can refer the reactance X1 into K square, X2 dash is equal to X2 by K square. And last we saw the equivalent circuit, and when we approximated the equivalent circuit, there were some approximations that we were making. No load voltage drop we neglected, then no load, primary, copper loss we neglected, then last overestimated IW and I mu, that is overestimating the core losses. So that is the approximations that we make if we shift the shunt branch from EMF to the terminal voltage side. So that is the equivalent circuit of the transformer. In the next lecture what we will say is how to find these parameters now. Now that I have the equivalent circuit, how do I find the values of this R0, X0 and R01, X01? That we will see in the next lecture.